We have constructed the I measure mu star, which is consistent with all Shannon's information measures. In this section, we are going to show that mu star can be negative. We are going to show that for n equals 2, mu star is always non-negative. For n equals 3, mu star is not always non-negative because the quantity mu star x1 tilde intersect x2 tilde intersect x3 tilde, which in information theoretic notations I x1 semicolon x2 semicolon x3 can be negative. Now for two random variables, the values of mu star on the non-empty atoms of F2 are all Shannon's information measures which are non-negative, namely entropy of x1 given x2, the mutual information between x1 and x2, the conditional entropy of x2 given x1. Therefore, mu star is always non-negative. Now for three random variables, there are 7 non-empty atoms of F3. First, we have those atoms that corresponds to the entropy of one random variable given two random variables. For example, entropy of x1 given x2 and x3. We also have atoms that correspond to the mutual information between two random variables given the third random variable. For example, the mutual information between x1 and x2 given x3. However, for the atom that corresponds to the intersection of the three sets, we have mu star x1 tilde intersect x2 tilde intersect x3 tilde, which in information theoretic notation can be written as I x1 semicolon x2 semicolon x3, does not correspond to any Shannon's information measures. In fact, we will show that it is possible to construct random variables x1, x2, and x3 such that mu star x1 tilde intersect x2 tilde intersect x3 tilde is less than 0. We now give an example that shows that mu star can in fact be negative. In this example, all entropies are in the base 2. Let x1 and x2 be independent binary random variables with uniform distribution. That is, the probability that xi is equal to 0 is equal to the probability that xi is equal to 1 is equal to 0.5 for I equals 1 and 2. Let x3 be x1 plus x2 modulo 2. It is easy to check that x3 also has a uniform distribution. Thus, the entropy of xi is equal to 1 for all I. It is also easy to check that x1, x2, and x3 are pairwise independent. Therefore, the entropy of xi xj is equal to 2, and the mutual information between xi and xj is equal to 0 for all distinct ij between 1 and 3. Now we see from equation 1 that x3 is a function of x1 and x2, so that the conditional entropy of x3 given x1 and x2 is equal to 0. Then, by the chain rule for entropy, we have entropy x1, x2, x3 equals entropy x1, x2 plus entropy x3 given x1 and x2. Now, entropy x1, x2 is equal to 2, and entropy x3 given x1 and x2 is equal to 0. Therefore, entropy x1, x2, x3 is equal to 2. Now for distinct I, j, and k, we have the conditional mutual information between xi and xj given xk by lemma 3.8 is equal to entropy xi(xk) plus entropy xj(xk) minus entropy x1, x2, x3 minus entropy xk. Now entropy xi(xk) and entropy xj(xk) are both equal to 2. Entropy x1, x2, x3 equals 2, and entropy xk equals 1. Therefore, the mutual information between xi and xj given xk is equal to 1. It then follows that mu star x1 tilde intersect x2 tilde intersect x3 tilde, which is equal to mu star x1 tilde intersect x2 tilde minus mu star x1 tilde intersect x2 tilde minus x3 tilde, which is equal to I x1 x2 minus I x1 x2 given x3, where I x1 x2 is equal to 0 and I x1 x2 x3 is equal to 1. Therefore, we conclude that mu star x1 tilde intersect x2 tilde intersect x3 tilde is less than 0. This shows that mu star can be negative. This is the information diagram for the mu star that we have constructed in example 3.10.